So, hello everybody and welcome to the third module of this course, where we shall be learning about Monte Carlo simulations, and in particular we shall model the Ising model, use the Ising model for our Monte Carlo simulations. Now, what is Ising model? It is basically a model Hamiltonian to understand ferromagnetic to paramagnetic phase transitions as one increases the temperature. Using these Monte Carlo simulations, by which we shall model the Ising model, we shall be aiming to understand the phenomena of phase transitions. So, the Ising model shows ferromagnetic to paramagnetic phase transitions, and the broad idea is that if you understand the phase transitions in the Ising model, one can extrapolate similar ideas. So, we can learn the language of phase transitions and extrapolate these ideas to understand other more complicated phase transitions behavior. Now, I understand right at the beginning I introduced a large number of terms with which you might be unfamiliar with. So, I shall basically go through each of these terms and explain what they mean. Okay. So, what does the word simulations mean? So, by simulations, the idea is to model a physical system on the computer, and as you change parameters like temperature, pressure, magnetic field, etc., on the computer, where these things are also modeled in a program on the computer, the system basically shows behavior, change in behavior analogous to the real system, and then you are basically trying to understand, model the system on the computer and understand its behavior. For that, one needs essentially the appropriate degrees of freedom. Now, suppose you are going to model the liquid gas transition, then you basically need to define the position and velocity of n particles in a simulation box. Of course, I shall discuss all these in further detail. Give the effective interaction energy or the Hamiltonian of interaction between the different particles of the box, and then these particles basically interact via this Hamiltonian and they move around in space. So, they collide with each other, they change their positions, they change their velocities, and then using appropriate statistical physics. So, you have specified the microscopic degrees of freedom, and using the language of statistical physics, one can calculate thermodynamic properties of the system and then compare with nature or with experiments. Now, if using the right, you are using the right Hamiltonian, you are using the right interaction, you are modeling it appropriately, your model simulations will show the appropriate behavior, and now you have access to all the microscopic degrees of freedom from which you calculate whatever thermodynamic properties you want to calculate and basically develop an understanding of the system. Right. Now, just to remind you, what does statistical physics do? It basically connects microscopic degrees of freedom, or you start from the microscopic physics and it gives you a mechanism to calculate thermodynamic properties of the system, which are typically measured in the lab. Okay. So, before we even discuss the Ising model, which is a model Hamiltonian to understand ferromagnetism, and before we actually talk about simulations, we shall basically revise, or since you might be coming from different backgrounds with different statistical physics 1 course, we shall discuss what is phase transitions, give you some appropriate background about the physics of phase transitions, and only after that background we shall discuss or write down the Ising Hamiltonian, discuss the physics of it, discuss ferromagnetic to paramagnetic transitions, and then we shall get down to the calculation or the simulation details. How are we going to model this model Hamiltonian on the computer to understand ferromagnetic to paramagnetic phase transitions. So, that is the plan. So, the first half an hour or more is going to be discussing phase transitions, statistical physics, and so on and so forth. Before I discuss phase transitions, let me tell you what do I mean by Monte Carlo simulations. Now, even in the first or the second module, you know that Monte Carlo method is essentially solving a problem using stochastic method. So, basically there will be a random number generator. So, even in our simulations and Monte Carlo simulations, we shall use a random number generator to access different microstates of the system. So, when we model the ferromagnet, we shall basically make our model system access different microstates, and how these microstates will be accessed, it will be a stochastic method using a random number generator. I already told you that Ising model is a model Hamiltonian, which basically shows or mimics the magnetic properties. So, using the Ising model we can understand the ferromagnetic phase transition, ferromagnetic to paramagnetic state as you increase the temperature of the system, and this is a good method to understand phase transitions. But let us first discuss what do I mean by phase transition, what is its basic behavior, what do you understand by phase transitions. Now, you might have already have had an intuitive idea with the meaning of the word phase. So, you know that basically when you have ice, it is in a solid phase, and when you increase the temperature it becomes water, or it goes to the liquid phase, and when you increase the temperature to at even higher temperatures above 100 degree centigrade, it becomes the gas phase. So, these are various states of matter, they have different properties, microscopically they have different symmetries, and when you change an external field, in this case the temperature, basically the system goes from one phase to the other phase to the other phase. You might have also known or heard about the ferromagnetic phase transition. So, you have all played with a bar magnet, and at room temperatures it shows finite magnetic moment. If you take a bar magnet, it likes to point along the north. If you suspend a bar magnet using a thread, it basically likes to point along the north pole, or rather the not the north pole, but the basically magnetic north pole. And you know that if you increase the temperature beyond a certain critical temperature, the magnetic moment, the magnetized state of that iron is lost. So, basically again when you increase the temperature, there is a phase transition from the ferromagnetic state to a high temperature state where there is no net magnetic moment. Microscopically, the spins or the magnetic moments point in all possible directions at high temperature, and how and why that happens is what we shall be exploring through our Ising model simulations. You might have also heard about the superconducting phase transition. There are some materials like mercury which at high temperature are conducting, but when you cool down the system below a certain critical temperature, the resistivity essentially goes to 0, the conductivity becomes infinite, and you say that it has changed from a normal metal to a superconducting phase. So, these are things which you might have already heard about. Let me introduce to you some phase transitions in some liquid crystals. These liquid crystals are the same liquid crystals that you might know about from liquid crystal displays, liquid crystal LCTVs, and there basically the arrangement of the molecules, and I shall discuss this in greater detail, goes from the isotropic to the nematic to the smectic phase. What are they? So, what are these things? What are liquid crystals and what are these phases? What am I talking about? So, basically the idea of liquid crystals, the constituent. So, the constituent of liquid crystals are essentially made up of long rod like molecules like these. Okay. And these are typically dispersed in a background fluid. These orange dots essentially denote a background fluid, and these rod like molecules undergo Brownian motion in the fluid, and they are pointed in all possible directions. Now, as they undergo Brownian motion, they are not only change their position from say here to here, but even the axis. So, you see if there is a rod like molecule, you can define an axis along the rod, and these axes along the rod also undergo Brownian motion, and basically the axis can point in all possible directions, and this is because of the bombardment of the background fluid. And then you say that it is in the so called disordered state. Now, if you increase the density of these rod like molecules in the system, what happens is these rod like molecules tend to orient themselves along a particular direction, say the z direction. Okay. So, in this state, which is called the nematic state or the nematic phase, what you have is the average orientation of the axis is along the z direction, but the position can change. So, the position is doing a Brownian motion. So, it can move from any one point in space to the other. The axis can also change, that is also doing some Brownian motion. Of course, there is some rotational Brownian motion, but on an average you see in this picture that the axis is all pointing along one particular direction. So, you see that there is change in symmetry from the so called disordered phase to the nematic phase, where there is no. So, in this nematic state there is no positional order. Yes, they can be in any point in the liquid, just like a liquid, but you have got orientational order. So, there has been a change of phase and there is a change in microscopic symmetry. There has been a change in order microscopically in the system. Now, if you increase the density of these molecules even further, and assuming that the molecules are all of the same size, they can go in the so called smectic state. In the smectic state, they basically not only point on an average along a particular direction, say the z direction, but they also align themselves up in layers. So, this is one layer, this is one layer, this is one layer. So, in a layer, the particles can move around within that layer freely like a liquid. There is an average orientation axis, of course, there are fluctuations, but there is an average orientation axis. So, in the x and y direction, assuming this is x and this is y, it is moving around in a liquid, but there has some order which has been picked up along the z direction. Okay. So, if you look at the density, you will see a density density of these molecules. There is some density modulation from here to here to here to here. So, there is increase in in the density here and lesser density of these molecules in between these layers. So, again, so previously you had examples where you had phase transitions when the temperature was changed, the solid liquid gas or the ferromagnetic or the superconducting, but here you see that when you increase the density of these rod like molecules, you are going from the so called disordered phase to the nematic phase to the smectic phase. Okay. So, while it is interesting enough to understand from a basic point of view, basic physics point of view, why these phase transitions or how these phase transitions happen, it is important to understand phase transitions also for industrial purposes. And here just for the fun of it, I give you an example where lack of understanding of phase transitions led to defeat in a war. So, Napoleon, when he basically attacked Russia 200 years ago, and he decided to attack Russia in the winter, basically the soldiers were wearing some coats. So, this coat had buttons which was made up of tin. Okay. And when he reached Russia to fight his war, Russia is far colder than the other parts of Europe. Basically, these buttons which were in the so called beta tin phase, and which is ductile and metallic and behaves like a normal metal, that underwent phase transition at lower temperatures into so called the alpha tin, and that is a powdery phase. So, basically the buttons became powders and fell off. Okay, and that was not very comfortable for, of course, the soldiers to fight in that freezing cold. Of course, I am not saying that that was the only reason he lost the war. The point I am trying to make is that understanding phase transitions also has implications and ramifications in the real world. So, you need to understand the properties of materials. Okay. With that background, with this basically examples of these phase transitions, let us focus on ferromagnetic phase transitions, and let us discuss about phase transitions in greater detail, where we shall basically discuss the ferromagnetic phase transition. Now, you already know, and you have all played with a bar magnet in all probability, where basically one has the so called north pole and then there is the south pole, and you bring two bar magnets together. Two north poles repel each other, and you know that the bar magnet is magnetized. Okay. Of course, you have also iron which does not show any magnetic properties, and that is because basically a bar magnet has domains. So, room temperature iron at room temperature is always magnetized, but you can also have iron where you have different domains, different regions within the bar magnet, where the magnetic moments are pointing along different directions, like this or like this or like this or like this, in different directions. So, that on an average you are seeing no net magnetic moment. But when you pass a DC field, or suppose you stroke a bar magnet with another magnet, then the magnetic moments and these different domains essentially start pointing along the same direction. So, as a result, you see a magnetized iron. But if you heat iron above 770 degree centigrade, which is 1043 Kelvin, you will see that the iron rod, a magnetized or iron rod, loses its magnetic properties. It does not show any net magnetic moment, and the question is how and why, what is happening within the iron that the iron is unable to show its magnetic properties. Similarly, if you have cobalt and if you heat it above 1115 degrees centigrade, then again it is ferromagnetic at room temperatures, but above this temperature it loses its magnetic properties. Right, it does not remain a ferromagnet anymore, and nickel is also a ferromagnet, and it loses its magnetism above 354 degree Kelvin. And we say that above these so called critical temperatures of 770, 1115 or 354, the iron or the cobalt or the nickel reaches a paramagnetic state. Now, I want to clarify and I want to emphasize that a paramagnetic state is not the same as a paramagnet. So, in a paramagnet, there is no effective interaction between the spins, and it does not show any net magnetic moment at any temperature unless you switch on an external magnetic field. So, what happens in this case in a paramagnet, Due to thermal fluctuations, basically all the magnetic moments in a paramagnet point in different directions, and as a result you see no net magnetic moment. These spins are not interacting with each other, or the magnetic moments are not interacting with each other. For a ferromagnet, there is an interaction between adjacent spins. Okay. So, that interaction always remains, but above a certain critical temperature given in these three cases, what happens is that the thermal fluctuations dominates over the ferromagnetic interactions. We shall discuss this in greater detail, and it behaves like a paramagnet, which means that there is no net magnetic moment between the spins, even though there is interaction between the spins or the magnetic moments in a ferromagnet, which tries to align the spins in the same direction. So, basically what I want to say, that in a ferromagnetic case, when you increase the temperature below a certain critical temperature, it loses its effective magnetic moment and it reaches the paramagnetic state, and that is not the same as a paramagnetic material. I just wanted to emphasize this. So, the high temperature disordered state is called the paramagnetic state. After this, before we go on discussing phase transitions in greater detail, I need to introduce the idea of an order parameter. Okay. So, what is an order parameter? It is a quantity which can be calculated or measured in experiments, and this quantity can be used to distinguish between the two states or the two phases. So, basically it is a quantity which will be 0 in one of the phases and it will have a finite value in the other phase. So, when we are discussing ferromagnetism, magnetization can be used, the quantity magnetization, the effective magnetic moment of the system can be used as an order parameter. At low temperatures, the magnetization, the average magnetization shows a finite value at 0 temperature. So, basically what is plotted on the y axis, you are plotting the magnetization, which you can define as the order parameter to characterize a ferromagnetic to paramagnetic transition. So, on the y axis there is magnetization, on the x axis there is temperature, and at 0 temperature basically all the magnetic moments in a ferromagnet will be pointing in the same direction. The magnetic moment will be the maximum, but as you increase the temperature, you will see that the magnetic moment slowly decreases, and above a certain temperatures called the so called critical temperature Tc, the magnetic moment will go to 0, right. For calculational purposes, so that is what you would measure in the, so this is what you would measure in experiments. For calculation purposes, one can also use the magnetic moment per spin, n being the total number of spins in the system, as the order parameter, and we can calculate what is the average magnetic moment per spin, and that will show some finite value at low temperatures, and above the critical temperature its value will go to 0. There are certain advantages in using this quantity. We shall discuss it as we shall go along. Okay. So, basically we would say that the magnetic moment here is finite and goes to 0 above the temperature, and it is an order parameter. And next what I shall introduce the idea of is kind of phase transitions. You have the so called the first order phase transitions and you have the so called second order phase transitions. I shall discuss that basically the ferromagnetic to paramagnetic transition at Tc is a second order phase transition. But what are first order phase transition and what is a second order phase transition? So, in a first order phase transition, thermodynamic quantities which are obtained from the first order derivatives of the free energy, they show a discontinuity. What do I mean by that? What are the first order derivatives of the free energy? Quantities like the average energy, the internal energy of the system. The magnetization, if you are talking about a ferromagnetic sample, the magnetization. If you are talking about a liquid gas phase transition, then volume per particle. These quantities, the average, the thermodynamic averages can be obtained by taking first order derivatives of the free energy or the Gibbs free energy, depending upon what ensemble you are working on. Why is that? We shall discuss it. And what is second order phase transition? Quantities like the heat capacity, the magnetic susceptibility or the compressibility, which are second order derivatives of the free energy or the Gibbs free energy. So, F being the Helmholtz free energy and G being the Gibbs free energy. These quantities like Cv, chi and compressibility are essentially second order derivatives of the free energy, and these show a singularity. Okay. For second order phase transitions, the quantities like energy, magnetization, these do not, I mean whatever be the relevant thermodynamic quantities, they do not show any discontinuity. Why did I say energy, magnetization, these are first order derivatives of free energy? Let me just quickly remind you, this is a quick recap. So, it is even titled StatMech reminders. Let me remind you that when we are discussing a system which is basically in the canonical ensemble, the average energy of the system can be defined as del del beta of beta times the free energy. What is beta? It is 1 by kBT. Okay. So, how do you obtain that? I shall just remind you that Z is the partition function. Statistical, you must have at least come across the partition function in your stat phase 1 course. Z is the partition function and is defined as the sum e to the power minus beta E I, okay, sum over I, where the sum is over all microstates that the system can access, and E I is the energy of each microstate. Now, if you can calculate the partition function, and in some cases, in the simplest cases you can, and in more complicated cases you can't, and that is why you do simulations. But in principle, if you manage to calculate the partition function, then you can write down the free energy F, the Helmholtz free energy F, as minus kBT of log of Z, log of the partition function. And if you can write down explicitly the if you can calculate the free energy, then by taking suitable derivatives with respect to beta, beta being again the 1 by kBT, kB being the Boltzmann constant, then you can calculate the average energy of the system. Why are you able to calculate that, or how are you able to calculate that? I shall just remind you that the average energy of the system can be written in by this expression. It is basically a sum over all microstates, energy of the microstates, and this is the probability of accessing e to the power minus beta E I by Z is the probability of accessing that microstate, right. This is the general formula. So, different microstates are being accessed with different probabilities depending on the energy of the system, and you do a weighted average of the energy of each microstates, and that is how you get the average energy. And that can be written, this expression can be written as 1 by Z del del beta, when you take a derivative with respect to beta, beta being as I told you 1 by kBT. When you take a derivative with respect to beta, you basically get this energy comes out, and I have put in a minus sign to keep track of the right the signs. This can be written like this, and then you since you are taking a derivative with respect to beta, you can pull it out of the summation sign. The summation is over all microstates, and if you can write that, you shall see that summation over I e to the power minus beta E I is nothing but the partition function which we wrote down here, right. So, immediately you can write this as 1 by z del beta of the partition function. 1 by z del beta can be written as del beta of log z with a minus sign, and log z ln z is nothing but beta times f. I am using this expression. I am just using log z and just basically writing minus k beta, which takes care of the minus sign. So, what I have shown here, which you should have done already in a StatMech course, that the average energy of the system can be written as del beta of beta into free energy. If you write beta, if you use this relation, you can also write this average energy of the system in terms of T square, T being the temperature, del T of F by T. I have done nothing but taken the converted this derivative with respect to beta with respect to temperature. Using very similar methods, please check it out, look up your StatMech book. The magnetization can be written as del F del B, B being the magnetic field. Okay. So, if you have a magnetic system, you take the first derivative with respect to B. Using statistical physics, one can show that the average magnetization can be written. You see that both average energy, magnetization, these are essentially the first derivatives of the free energy. And what I had said, that first order transitions are those where the first order derivatives of the free energy show a discontinuity. Now, in a ferromagnetic to paramagnetic transition, the first order derivatives of the free energy, the average energy and m, they do not show a discontinuity. What is seen is it changes continuously, but C v, which is the second order derivative. So, what is C v? It is basic del u del t, del u is the u is the internal energy, which is basically a measure of the average energy of the system. So, C v or chi is the basically magnetic susceptibility, del m del beta, right. So, these show a singularity. Okay. So, the ferromagnetic to paramagnetic transition is a second order phase transition, because the first order derivatives do not show any jump. If they show a jump, as when water changes to gas, when you increase the temperature, it is associated with a latent heat. Okay. There is a jump in the first order derivatives, is associated with the latent heat, but a ferromagnetic to paramagnetic transition is essentially a second order phase transition.